Oh, hello. This is really cool. Come and take a look at this. Today I'm going to talk about drifting methanol masers in the massive star forming region G962 plus 0.20. And when I mean drifting, I'm talking about its velocity. Don't let the name fool you. Those are just the galactic coordinates. This is a really interesting source. Carl discovered that this source had the brightest methanol maser in the galaxy in 1991. You can see here it's 5,000 Janskis. And at the 92 conference in Washington on masers, he referred to it as the mother of all methanol masers, in reference directly to the First Iraq War. Now, I want to give a bigger shout out to Carl regarding this. Now, at Hartebeesthoek, it's a small 26-meter telescope. We don't have the sensitivity of the larger ones, and we didn't have the receivers. But this transition, because it's so bright, it gave us the ability to do so much more observing at Hartebeesthoek. We were doing other masers that we monitored, OHIRs, but this really launched the star formation side of the spectroscopy at Hartebeesthoek. And it led to some of the future discoveries that came from it. So I really want to give a shout out to Carl again. I can't say enough about how important this particular discovery was as it relates to the science that was carried out at Hartebeesthoek afterwards. In 2003, it got even more exciting. And of course, in 2003, Sharmila Goodhart discovered periodic methanol masers. This was absolutely astounding. You can see here her 99 to 2002 data that she published in her paper in 2003. Now, I want to make something very clear that people don't really appreciate when unless you do long-term monitoring. Sharmila would have known that this source was periodic in 2000. She would have known it was periodic by the time she saw the third flare. Okay? She had to wait until she saw the sixth flare to confirm the periodicity so that no one would doubt her. And can you imagine what it must have took for her and Mike and all the others at Hartebeesthoek to try to contain this by not telling anybody? I mean, they would have been just so excited. They wanted to get out there and tell the world. And it would have been difficult. Would have been really hard. They might have gone to conferences and presented results. I'm sure they did. I wasn't involved back then. I didn't know. But this would have been an amazing time to be at Hartebeesthoek, to have this poor woman, a graduate student, sitting on what would become probably the biggest discovery in star formation as it relates to masers since some of the earlier transitions. So it really was a big discovery. And again, done by a small 26-meter telescope looking at a really bright source. It made it easy for us, and it makes it easy for all of us to do this kind of research. Anyways, I just think about that. I just think how excited Sharmila must have been by the time she saw that third flare and what she had to sit on before everybody else would believe her. She would have literally been sitting on her seat every day for 240 days waiting for the next flare. It would have been good fun. It would have been good fun. And again, I give a big shout out to Sharmila. She did a great job. That's what astronomers do. We look for these things, and we got to keep doing that. In 2015, I returned to Hartebeesthoek to head up their spectroscopy program. There was a huge problem with it after, of course, Mike Gaylord died, because there was no one left to lead it. And my good friend Ludwig Kombrink asked if I would come back and help out, and I was very keen to. I always loved working at the observatory. Any of you who have worked at observatories will understand why I say that. There's just nothing better than being at an observatory, and I enjoyed going there. And unfortunately also, at the time that after Mike had died, Sharmila Goodhart had graduated and had left to the SKA program. So it left a massive hole in the spectroscopy program at Hartebeesthoek, which was one of their major programs. And certainly, well, we'd like to think it's a significant program around the world too in terms of what we contribute, but that's just a little bit of bias on my part. Anyways, during the time that I arrived there, I found that there was lots of students would show up and they would want to shadow astronomers. And so they always asked me, because I seem to be the most friendly, if you can imagine. I don't think people would describe me as friendly, but never mind. But I enjoy talking to students all the same. And I'd give them tours of the observatory, and I would talk about careers in astronomy and the pitfalls of it and how difficult it can be sometimes, and you have to see through all that. I think I've given videos on passion, patience, and persistence, and those are the three things I kind of look for in a student. So of course I would impart that knowledge to them. Are they really passionate about it? Otherwise, don't do it. Well, anyways, one thing I did find a little uncomfortable was I spend large periods of my time staring at my computer, staring at data. I'm sure most of you know what I'm talking about. And basically, when they're shadowing me, they're sitting behind me, looking over my shoulder, looking at the back of my head. And it makes me very uncomfortable. I don't enjoy it. And so I thought to myself, no, this isn't going to work. I got to find a way to put them to work. If they want to know what it's like to be an astronomer, the best thing you can do is give them data and let them play. And that's precisely what I decided to do. So I took them off to our computer lab, I sat them down in front of a computer, I gave them a whole bunch of data, and I showed them how to process heart rail data, doing baseline fitting, Gaussian fitting, all those kinds of things. And then I also showed them how to automate it and whatnot. So they learned the process of processing heart rail data. And with it, I would always tell the students one thing: never sit here for 8 hours just processing data. Always stop after an hour or so, put the data into a Excel spreadsheet or whatever you want to do, and just look at it. Just marvel at it. Look at the spectra. Create a time series. So I showed them how to do those things as well. Anyways, long story cut very short, I had a couple of very good students, but one in particular, Joel Polson, showed up in 2017, in fact. And I put him to work on this source, 0962. I'd always been interested in this source because we had monitored it in the early 90s, along with other sources that we had a great deal of interest in. And we never noticed the periodicity, whereas Sharmila did, and good for her. Now, I always wondered why I never, and of course, the answer in the end was our cadence wasn't very good. All right? But I thought to myself, I haven't looked at the raw data at all for some time, so let me put a student to it, and I put Joel to it. So Joel processed this data. This here is the time series that Joel basically produced and showed me, and it was pretty exciting stuff for him. Certainly I was impressed by it. I thought, wow, this is pretty cool. High school kid, nothing wrong, finds a new feature that's periodic. So Joel produced this time series, which I've shown you, and he says to me, okay, obviously he's found a periodic methanol maze. I thought that's pretty cool for a high school kid, you know, and for me, you know, if you make a small contribution in some way, shape, or form, you know, if I was to publish, I would put his name in the paper, and of course, we did publish, not necessarily because of that one feature, but I did put his name in the paper. So here's a high school kid now, has a publication in Monthly Notices. So all of us can dream to do something at that age. He was 17, I think, or 18 at the time. It was pretty good. Anyways, but what I wanted to do is I thought to myself, well, okay, if there's one feature that's new and it's periodic, what if there's more? So I thought, well, let's find a way to look at the data so that we can, you know, get a quick feel for it. And the obvious answer is dynamic spectra, right? So you have these multi-column files with successive observations. The y-axis is velocity, the x-axis is the time series, and the contours are the strength of the masers. Pretty simple stuff, but it's a very easy and a very quick way to look at your data, rough and ready, and see if there's something interesting in it. Here we've blown up the dynamic spectra so it's easier to look at. You can clearly see that the source is still extremely bright as first discovered by Carl Menton. I've got it in logarithmic scale, probably to try to bring out some of the smaller features. Never mind. And obviously periodic, that was seen by Sharmila Goodhart. Now we can clearly see Joel's feature at 4.8 kilometers per second is periodic. Very easily seen in dynamic spectra. Also, something else that surprised me was the fact that it's redshifted. At the beginning, I could easily fit it with a single Gaussian, which gave me confidence that it was an independent feature, and likewise I could fit a single Gaussian to the feature redward of it. But as I said, you can see here it's velocity drifting. And if we look a little closer, maybe if I poke you in the eye, you might notice that there's a very weak set of masers up here at 8 kilometers per second. In fact, they too were found to be periodic, so they were new features also found to be periodic. The last thing I want to point out in this diagram is you start noticing that the velocity drift is not simply in Joel's feature. We can see one down here very easily at -3 kilometers per second. And if we look a little closely, we start seeing them here in the +2 to +4 range as well. And some of these in here also. So this was very surprising, very surprising. So of course, once you notice that the source has, something interesting in it, the data has something interesting in it, in this case, the drifting masers, we want to be able to present them in such a way that anybody else could see them as easily, rather than having to stare for hours or say, yeah, that looks interesting. Well, the easiest way to do that is to break it up into velocity regimes. So what I'll do here is I'll break them up into the redshifting component, the neutral component, that is about the velocity feature at +1.2, the strongest feature, and then the blue shifting features below that in a separate panel. And in each case, I can then adjust the intensity range to draw out the features better and let you see them better. So now we can clearly see that Joel's periodic source is redshifting. It was separate here from the source at 5 point whatever, and it's basically becoming more and more line merged with that feature. But if we look closely at the other panels, we start noticing other features, such as this at about 3.8 kilometers per second, one at 3, one at 2 point something. They're all redshifting. And then when we look down below, we see one at -3 is blue shifting. We get some evidence of another source here around 0 kilometers per second, blue shifting, and then one at +0.5. So there's lots of features red shifting and blue shifting here. I'll try to make it easier still. I've overlaid the velocities associated with the maxima for each feature in each epoch of observation. So I've overlaid the associated velocities with the peaks for each feature in each observation. And you can see the lines, but of course that can become a bit confusing. Well, what I'll do is I'll just take the background contour maps away, and then let's take a look at it. This is the really cool part of this whole process. Once we've removed the dynamic spectra and we fit these lines, we now know that all the sources that are redward of +1.2 are redshifting, and all the features that are blueward of 1.2 are blue shifting. So you have this systematic velocity drift. Well, that was and is very surprising. I didn't expect to see something like that. So this is a really interesting source. It's the brightest methanol maser in the galaxy, found by Carl Manta in 1991. It's the first periodically varying methanol maser, found by Sharmila Goodhart, 2003. And now it has systematic velocity drifts. We think might be the result of either a precessing disk or the masers lie in the region of the disk that's infalling. But we're not 100% on that. That's really just a guess, okay? And something else I haven't shown, but we have the associated 12.2 gigahertz masers that have similar velocity features that are also systematically velocity drifting. So it really does confirm that this is not just a random chance event that we saw a bunch of masers, some varied. It would be highly unlikely. This really is a very interesting source and worth continuing monitoring, and we will carry on monitoring. And I'm willing to bet in the future, maybe even after I'm dead, we're going to find something interesting in this source. So this is interesting. This source is interesting. And this isn't the only interesting source, obviously. There's probably a great many. The surveys that have been done have shown that there is 1,000-odd star-forming regions. That number's probably even higher than that, even just in our Milky Way, never mind extragalactic sources. But in order to monitor so many sources, no single facility in the world can do that. Some will do a great job looking at hundreds, such as our friends in Japan. Others, like ourselves at Hartebeesthoek, we look at a few. We look at tens. And we look at them at many transitions. But we don't get enough coverage obviously. So we really do need to have an organization, which we have now, called the Maser Monitoring Organization. The M2O helps to coordinate the small facilities around the world. Look at the work coming out of Pushna, Russia, or the Polish group, the Italians. I mean, the Japanese monitoring is exceptional. And even some of the older facilities, such as Atipatinga in Brazil, some of the results that came from there were really quite exciting. And they found things. And they found things because they looked for long periods of time. So, you know, we need to work closely together to help one another, to look at more sources, at more transitions, more frequently, and for very long periods of time. We're going to need lots of telescopes to do that. Thank you. What's in your data? The GERAF Foundation will produce more videos like this. Please like, share, or subscribe if you enjoyed this video.